After studying this module, you shall be able to know in brief about spectroscopy, also learn in brief about IR spectroscopy. You will be able to define vibrational modes and normal modes of vibrations, learn the basics of IR spectroscopy, learn about the interaction of electromagnetic waves with the molecules, and you will learn also a block diagram oblique instrumentation of IR spectroscopy, and also some basic parts of instrumentation and IR sources will also be mentioned in this module, though the details can be obtained from number of other books, but here I will only deal with these small things. Now, in earlier modules we have studied about the symmetry of the molecules, their point groups, that is to which they belong, different types of symmetry elements present into the molecules, how symmetry operations are generated, and we have also seen that it is the symmetry operations that constitute a group, how to represent a group using various functions as the basis, what is the reducible representation, how it can be reduced to irreducible representation, that we have learnt in great orthogonality theorem. We have also learned about the character table, which is a unique for a particular point group, and why these are important to chemists. Now, we will make use of all this knowledge so far gathered on molecular symmetry and group theory in dealing with chemical applications of bonding, molecular orbital formation, vibrational spectra of transition metal complexes. Now, in this module, we will discuss vibrational spectroscopy in light of symmetry of the molecule. The symmetry of the molecule and solid is very important and very powerful tool in the hand of chemist for understanding bonding and physical properties. Infrared spectroscopy is one of the most important analytical techniques available to scientists. One of the great advantages of infrared spectroscopy is that any sample in any state may be investigated. Ligands, solution, paste, powder, films, fibers, gases and surfaces can all be investigated properly and with accuracy. Infrared spectroscopy is a technique based on the vibration of the atoms into the molecule. An infrared spectrum is commonly obtained by passing infrared radiation through a sample and determining what fraction of that incident radiation is absorbed at a particular energy. The energy at which any peak is in absorption spectrum appears corresponds to the frequency of vibration of a part of a sample molecule. The point group theory of molecular symmetry will now be used for interpreting the vibrational spectra of the molecule. That is, we will also go about their activity of the vibrational modes. What is the role of symmetry in vibrational spectrum studies? The presence of certain symmetry in molecules greatly reduces the efforts in predicting the molecular properties of the molecules. In earlier chapters, we have seen that how tau 3n can be obtained and reduced to irreducible representation of the point group to which the molecule belongs. Now, in this module, we will make use of this principle to have good deal of information about IR and Raman spectra of the molecule. Vibrational spectroscopy, that is IR, and Raman spectroscopy are the most common vibrational spectroscopies for assessing the molecular motion and fingerprinting species. Routine energy range of IR Raman is from 200 to 4000 centimeter inverse. One of the practical uses of the point groups and group theory for the inorganic chemist is in predicting the number of infrared and Raman bands that may be expected from a molecule. Spectroscopic technique all work on the principle of that under certain conditions, materials absorb or emit energy. Different spectroscopic techniques operate over different limited frequency ranges within this broad spectrum. Depending on the process and magnitude of the energy changes, the infrared region of the spectrum encompasses radiation with wave number ranging from 1 to 800 to 10 centimeter inverse, or wavelength from 0.78 to 1000 millimicron. The infrared spectrum is divided into near, mid, far and infrared radiation. The various energy ranges for these ranges. That is, in the near, it goes from 1 to 800 to 4000 centimeter inverse. For middle, it goes from 4000 to 200 centimeter inverse. For far, it goes to 200 to 10. Commonly used region is 4000 to 600 centimeter inverse, which is commonly the region. Now, let us go to define normal modes of vibrations. The complex vibration of a molecule are the superimpositions of the relative simple vibrations called the normal modes of vibration. Each of these vibration motions involve the displacement of the atoms or deformation of angles. These independent displacement or deformations are called normal modes of vibration of the molecule. These are generally divided in bond stretchings, angle deformations. Each of these vibration modes occur at characteristic energy or frequency, which is dependent on the strength of restoring force, called as restoring force constant. Each normal mode of vibration has a fixed frequency. It is easy to calculate the expected number of normal modes for a molecule made up of n atoms. For n atom molecules, the degree of freedoms are 3n. Out of these, we have to take care of 3 translational motion along x, y, z axis and 3 rotational degree of freedom about Rx, Ry and Rz rotation axis. A mode in which all atoms are moving in the same direction is equivalent to moving the molecule in that direction. A mode in which atoms move or rotate, change their orientation of the molecules. There are 3 rotational modes for nonlinear molecules and 2 rotational modes for linear molecules. These motions also occur when molecule absorbs IR radiation. These 3 translation and rotational modes are shown. That is, here a triatomic molecule is given. In translation motion, what we see, the whole molecule moves in one direction. Either it moves along z direction, or it moves along x direction, or it moves along y direction. Similarly, in rotational modes, the whole molecule rotates about z-axis, or rotates about x-axis, or rotates about y-axis. These are shown as follows with the help of the model. Let us take triatomic molecule. Here I will take the example of water molecule. Black ball shows oxygen, these are the hydrogens. Now, when I am saying translational motion, this molecule as a whole, it can move along z-axis, or it can move along y-axis like this, or it can move along x-axis. That is, when all the three atoms, they move in one direction. This atom moves in this direction, this atom moves in this direction, this atom moves in this direction. It means all the molecule moves in this direction. If this atom moves in this direction, this atom moves in this direction, this atom moves in this direction, all molecule moves in this direction. Similarly, this atom moves in this direction, this atom also moves in this direction, this atom moves on the, it means the whole molecule moves in this direction. Now, similarly, in rotational motion, the whole molecule, it can move along about z-axis like this, and this happens when this atom moves in this direction, this moves in this direction, this moves in direction, the whole molecule will rotate like this. Similarly, as shown in the molecule can move along your y-axis, that is, it can move like that is, and it can also move along your x-axis. This is my x-axis, it can move like this, and all these motions of the various atoms. So, we are having now 3 rotational motions and 3 your translational motions for this molecule. For linear molecules of n atoms has normal modes as 3n minus 5, as rotation about molecular axis is generally forbidden. For nonlinear bent molecule of n atoms has normal modes of vibration as 3n minus 6. The symmetries of the normal modes can be classified with the help of symmetry and group theory. Now, let us take linear molecule as carbon dioxide. Now, in the diagram I am showing over here the stretching, anti-stretching, and there are 2 types of bending. That is, in which the whole molecule, if I am take, both these bonds go up, that is, it is bending like this up. Similarly, it can bend towards you, these 2 bends can bend towards you. So, in this molecule we are having symmetric stretches, it is stretched equally both sides. In the anti-symmetric, this is stretch and this is not stretch, and like this there are 2 bending modes. For water molecules, we are having again stretching, then anti-stretching, and then angle deformations. This has 3n minus 6. This is my, if both the bonds are stretched equally, these are equally stretched. If one of the bond is stretched and this is not stretched, this goes inside, or angle deformation, it is moved inside like this. So, in this nonlinear we are having 3n minus 6. Now, various bond stretching and bond angle deformation, which can be made as basis for representation in Ir spectroscopy figure, we are having now. Let us take again water molecule and try to write down various types of motions into this. If I take this water molecule, if my water molecule rotates like this in the plane, it is just like in the same plane, it is called rocking. That is, it is rocking like this. And if the bond angle decreases or increases, that is, this atom and this atom, they move towards each other, then they stretch it like this. It is a scissoring. Then, if this whole molecule goes out of plane like this, like this, that is whole molecule goes out of plane and back, it is called wagging. Then we have the twisting. If one of the atoms comes towards you and another atom comes towards me, then it is called twisting. That is like this. One of the atom goes towards you and one of the atom goes. Then we have this stretching. In this molecule, symmetric stretching and anti-symmetric. That is in this water molecule, triatomic molecular, I have shown you the various types of motions which are given, that is deformation of angles, stretching of angles. So, we have now rocking, scissoring, wagging, twisting, symmetric stretching, anti-symmetric stretching, all these vibration modes are. Now, all these modes of vibrations vibrate with different frequencies and these require different energies to be activated. How the values of these characteristic energy or frequencies are obtained, that is the next point. There are two complementary techniques available for this, that is for studying the vibrational modes etc. of the molecule. There are two complementary techniques. All these modes of vibrations, as I have shown you earlier, they require different energy, and how these values or character energies are obtained is further our work for doing this. There are two complementary techniques available for this: infrared spectroscopy IR, Raman spectroscopy R. Both these techniques, when used together, provide lot of information about molecular bonding. Let us mention in very brief the basic principle of this technique. In this model, I will just take up the IR technique. The fundamental difference between IR and Raman frequencies techniques is that in the former, it is the absorption of the photon which is studied, while in the latter case, it is the scattering of the photon, elastic or non-elastic, is studied. Detailed discussion is not the part of this model. However, I will mention some fundamental of these techniques in brief. Let us take IR spectroscopy. Infrared spectroscopy of a sample. If a sample is irradiated with infrared light, then those frequencies that match the corresponding frequency of vibrational mode will be absorbed. That is, the absorbed frequency can be measured during infrared radiation on the molecule. Rotational motion of the molecule, translational motion of the molecule, vibration of the bond in the molecule, angle deformation into the molecule do occur, depending on the frequency ranges. Rotational and translational motions complicate the investigations. So, we have to account for these motions. In order the absorption of IR radiation by the molecule occur, two conditions must be satisfied. Number A, dipole moment of the molecule must change as a result of molecular vibration. The change in dipole moment allows the electric field component of electromagnetic radiation to interact with the molecular's electric field moment. The symmetric molecules do not change or do not have dipole moment during vibrations. So, they do not interact with the electromagnetic radiations, and thus these are IR inactive. Second, the frequency of IR radiation must match the natural frequency of vibration of the molecule, that is match with the fundamental mode of vibration. If there is a mismatch in frequencies, there will be no absorption of IR radiation. The three types of molecular transitions may occur during IR radiation, that is when molecule is exposed to IR radiation. When a molecule rotates about its center of mass, about any of the axes, the electric field component fluctuates. Due to this fluctuation, interaction between external electric field and internal natural electric field absorption of IR radiation may occur. The transition energy range is of the order less than 100 centimeter inverse. Due to this, vibrational peak in IR spectrum is further divided and thus complication arises into the investigation. Secondly, vibrational rotational transitions. This type of transitions may arise due to molecular electric dipole moment caused by the combination of bond vibration and molecular rotation. In the third case, in mid-IR region, most of the important vibrational transition occur. This frequency is of the order of 1300 to 675 centimeter inverse. In IR spectroscopy, quanta of radiation in IR regions have energy comparable to those required for vibrational transition in the molecule. The energy of the molecule is the total sum of various energies, which are shown over here. E is equal to E electronic, vibrational, rotational, translational, like this, magnetic. The E electric energy of the electrons of the molecule, E vibrational is the vibrational energy of the molecule, that is sum of the all vibrations of the atom. E rotational is the rotational energy of the molecule, which can rotate about 3 axes. E translational is the translational energy of the molecule, which is due to the movement of the molecule as a whole, movement. And E magnetic nuclear is the nuclear energy. The technique is based on two fundamental principles or laws, that is Hooke's law and second is Frank-Condon principle. According to Hooke's law, a diatomic atom may be assumed to be equivalent to a system of two masses A and B joined by a spring, or a spring hooked to a wall. That is, A and B are attached to each other, or A is attached to the wall. These are shown in this here. Now, if A and B are stretched and then allowed to leave, or if A is stretched, which is attached to the wall, then it will start vibrating about equilibrium position. And Hooke's law is applied to this. Hooke's law is F is equal to minus Kx. F is the restoring force acting on the system to bring back it to original position, where x is the distance from the equilibrium position. K is the restoring force or force constant, which describes stiffness of the spring. Negative sign means restoring force. Diatomic system A, B may be treated in similar manner. The restoring force that acts on two atomic masses is related by delta E is equal to h upon 2 pi under root k upon mu, where delta is the energy difference between ground vibrational quantum state and the first excited vibrational quantum state, that is E nu 0 to E nu plus 1. Nu represents vibrational quantum state. K is the force constant and mu is the reduced mass. Mu is equal to MB upon MA plus MB, where MA and MB are the masses of the SM A and B respectively. Since most molecules are in nu 0, yani ground state of the molecule, and thus most transition will occur from nu V0 to nu 1. Frequency corresponding to this transition is shown by fundamental frequency as shown into that is, it is a shown a diagram in which various transitions are shown. Therefore, first selection rule in IR spectroscopy is the absorption of radiation will occur for transition for which delta nu is plus minus 1 only. And the second rule says that the electric field component of the electromagnetic radiation in the IR region will interact with the electric field component of oscillating electric field dipole moment into the molecule as it vibrates. Any change in dipole moment or change in direction will give different oscillating field components of the dipole moment, which can interact with electric field component of electromagnetic radiation, and the absorption of radiation can occur. The transition 1 in the above diagram is a fundamental frequencies corresponding to a normal mode of vibrations. Transition 2 and 3 in the figure are not fundamentals, and these are the first and second overtones of the frequencies. These will be discussed in the later modules. The intensities of overtones are generally less than the fundamental frequency. Though at molecular level it is not so simple, and this model does not hold good, and there are deviations from this model. According to Frank-Condon principle, transition tend to take place between two vibrational states in which nuclear configuration remains same in both these states, and these tend to occur when nuclear kinetic energies are very small. Most common energy sources in IR is Nernst Glover or incandescent wires. Factors increasing the number of absorption bands. Number 1, overtone absorption bands occur at frequency which are multiples of the fundamental frequencies. Combination bands are observed when two fundamentals vibration interact due to symmetry equivalence with each other and influenced by the radiation of the combined frequency. Vibrational rotational bands are found with single vibration band and occur at low and high frequencies. Complex gas IR spectra are due to these vibrational rotational bands. Number 4, harmonic coupling bands are observed due to coupling of adjacent groups of nearly identical oscillations. Factors limiting the number of absorption bands. No change in dipole moment due to the symmetry of the molecule. Degeneracy. Vibrational frequencies are located too closely, or third, weak absorptions. Detailed discussion of this is not the scope of this module. Now, is given in the block diagram of a common IR spectrometer. In the block diagram, the main parts of an IR spectrophotometer are IR radiation source, dispersing elements and diffracting gratings, optical mirror systems, IR radiation detector. That is, after the source radiation, then there are the dispersing mirrors, etc., which allow this light to pass through the reference and sample. After passing through this light goes to the detectors and then it is detected. Now, the IR radiation from source after reflection at flat mirror and rotating mirror pass through references and samples. Transmitter light is amplified and detected by our IR detector. The detector, these are three categories of detector: thermal, pyroelectric and photoconducting. Again, this will not be discussion part.
Let us see an animation which depicts the working of an infrared double beam spectrophotometer. A light beam is generated from an infrared light source which is then separated into its component wavelengths by a diffraction grating. The beam is then split into two parts by a beam splitter. Half of the beam is passed through the sample cell and other half is passed through the reference cell. Then the beams are collected and analyzed in a detector, and the signals are then digitized. The detector records a graph between absorbance versus corresponding wavelength. The spectrometer electronically subtracts the absorption of the pure solvent from the absorption of solution and measures the absorbance or transmittance due to the compound itself.
Now, in this module, we have discussed in very brief about spectroscopy, information about IR spectroscopy provided, normal vibrational modes have been defined, and basic of IR spectroscopy has been discussed in very brief. In further modules, we will learn how molecular symmetry and group theory plays an important part in predicting or in finding the active vibrational modes into the molecule.